then you're thinking of this vector as Cartesian in the sense that it's x, y, z, even though you're using, in this case, in the case of this first drawing that we have, you're using the cylindrical coordinates as your parameters, but you're not, your vector is still Cartesian. If you wanted to use cylindrical coordinates to draw this figure, then you would not use r cosine t, or theta, which is x, r sine theta, which is y, and then you're saying that z is r square. You would use the actual cylindrical coordinates. You'd do r theta and r square for the z, and then say coords equals cylindrical. So most of the time, what we're doing when we're parameterizing to draw surfaces with these vectors is using them as Cartesian vectors in the sense that they are x, y, z, even though we might be using parameters which are the cylindrical coordinates like r and theta. I'm using the letter t for theta, so I don't have to spell it out. And then I have limits on r and on the angle, and either boxed axes or normal, and one style or another. And you see what you have with this thing, which is problem 1 in section 16.5, is a basket sort of thing, where the cross-section or intersection of the basket with any plane to form a cross-section would be parabolic. You see that the third component of that vector, which is z equal r square. So that's like the formula for a parabola, like z equal x square, z equal y square. And so then I did it again. It's the same thing, but I didn't say style equals wireframe, and so then you see the other style. Now, if you want to use these actual cylindrical coordinates, you can either do cylinder plot, as I did, or you can say plot and write your vector as I did at the bottom of the first sheet, and then say coords equal cylindrical, so you have two ways you can do it. So you see the cylindrical coordinates are r and the angle. I'm using t for theta. And then the third one is z equal r square. And because I said cylinder plot, or might have done it with plot and coords equal cylindrical, you get the right picture. But if you entered rt and r square and did not either do cylinder plot or coords equal cylindrical, you would not get this picture, because Maple thinks this vector is Cartesian unless you tell it it isn't. Okay. And then the next one, I just drew a quarter of it. That's the only difference. Then you notice that I did plot 3D and then coords equal cylindrical, and still have the same parabolic cross-section wastebasket, if you want to think of what that big thing is, at the top of the next sheet of paper. We're looking at Maple pictures here that go with section 16.5. And then you can always draw these things with implicit plot. Implicit plot 3D for surfaces, and write your equation with the Cartesian coordinates, z equal x squared plus y squared, you see, which is z equals r squared. And then you have to get limits on all the variables you name. And when you enter things as an equation like this, you have to use implicit plot, and you have to put what the TI calculator folks would call an X range and a Y range and a Z range in. And I have a piece of it there. And then the next one is the same sort of thing, but by extending the range, I get the familiar picture. Okay, so I've done this same problem several different ways, but what I'm trying to get at is that where we're going today is with this idea of writing a vector, the tip of which traces out our, okay, thank you, the tip of which traces out our surfaces, and I'm trying to make the point that for the variables, you might use either the variables of cylindrical coordinates or the variables of spherical coordinates, but if you're putting them in as expressing x in cylindrical coordinates or expressing x in spherical coordinates for your first component, and then the expression for y is your second component, then you're still working with a Cartesian type vector, which is usually going to be the case. So look here at the projection of a tile that's up on some curved surface down, say, in the XY plane. If you want to do surface area, what you want to do is you want to think of your surface tiled with green tiles, let's say, and you get your area by finding the areas of their projections and then integrating over the plane into which you have projected. So we're thinking of K in the usual way, and then gamma is the angle between K and what would be the normal to the tile. And so you could think of vectors, say a point here like this, and a curve C1, and a vector that would be along the edge of the tile, which would be in the black. I'm not sure how well that shows. And then you have in the blue the tangent to the curve at this point. And then as you come out, remember, I'm thinking of the surface as something like a sphere, for instance, that's bending down, whereas I'm thinking of what is in black here, where my stick is, as then a straight line that it ends up being up above where the curve is, or where the tip of the blue arrow is, as you've moved out on the tile. So there is also a vertical here, which would be dz, which, if you're thinking of this curve C1 as if it's parallel to the xz plane, then the slope of the curve would be partial with respect to x. And the dz would then be the slope, which would be the tangent of the angle where my stick is, where I'm tapping the board, times dx. You could do the same thing with a tangent T2. The bases of the T1 and T2 arrows would join back here at this point up on the surface. And if you thought of curve C2 as if it were parallel to the YZ plane, then your partial with Y would be the tangent of the angle corresponding to this one that would be over on this side. And the dy would be partial with Y. The dz rather would be partial with y, f sub y dy. So then the normal to this tile, which would be n, in green here, this vector, times ds, which is the actual magnitude of the area of this little tile, would be the area, the vector area of the green tile. So its magnitude is the number value, and then the orientation of the normal makes it a vector. So that would be the cross product of the two vectors that are its edges, because that's our formula from chapter 12, or I think chapter 12, yeah, of the area of a figure where you have a vector on each of two sides, like a parallelogram. You take the cross product and you get a vector perpendicular to your figure, and the magnitude is the area. So I'm doing that same thing. Well, if you take the cross product then of these two vectors, which are the lengths of the edges of the tile, I have set up my cross product here, and if you work this out, as always, you see what you're going to get. You'll get 0, you'll get 0, you'll get k, and then coming back the other way, you'll get f sub x and f sub y. So you get minus fx, because with the orange you are subtracting, minus fy and 1 dy dx, which you should remember having seen in chapter 14. This is the same thing as the gradient, as we called it then, of z minus f of xy. Because you see, with the gradients, you remember you take the partial with x, which is there, and the minus sign is there, comma, partial with y, which is there, comma, partial with z, which is there. So you can think of something like this and come out with the conclusion that if you take the gradient of this expression, where your surface is z equal f of xy, and multiply by dy dx, you'll get the vector area of a representative tile that's up here on the surface. And more than that, then, you can get your unit normal, because that'll be this vector over its magnitude. Okay, so the magnitude of this is the square root of this square plus that square plus that square. And so as I've that this is the magnitude of this gradient of z minus f of xy. So what does this have to do with connecting this area to its projection? Well, that goes back to chapter 12 and the projection of one vector B on another vector A. And so we'll pursue that in just a second. But I have a handout. On the one side, you see the cross product problem, and then that the unit normal is like this, which is the same thing as saying this vector over that. And then if you turn the page, you see that I'm what you see matches more or less with what I'm starting to do here. So now I'm thinking of the vector area of the green tile as my vector B. So notice the color scheme. And I'm projecting on vector A, which would be the area down here, which would be K, which is the normal here, and dA, which would be the dy dx. So our formula from chapter 12 for the projection of a vector B onto a vector A, that we call the vector projection, would be B dot A over A dot A. So it's the ratio of these dot products times the vector that you're projecting onto, the one on the floor. And so having identified A and B in this way, I'm just following this formula. And so you see my quotient of dot products, and what I'm projecting onto is this vector A. And on the other hand, what you really get down here is the same thing again, this vector area, which is dA in magnitude, and K is its orientation. So I actually have the K dA on both sides. So I have it here as I follow the formula. See, I have the N dot K, and that's a number, and that's a number. So I have those numbers. I have K dot K, which of course is 1, and the number and the number, times the vector that I'm projecting onto, so that's this, and this is what the projection is. So, of course, what you have is the same vector here and there, so therefore this coefficient has to match this one, which is what I'm saying. You're matching your K components, and then you're doing whatever algebra you can, that cancels, and K dot K is 1, and notice that N dot K, where your N is like this and your K is like this, is, since these are unit vectors, the N dot K is the cosine of the angle. Dot product's the magnitude of the vectors, cosine of the angle, but if they're unit vectors, it's just the cosine. So that's what I've said there. So what it leaves you then is that the cosine of the angle between the normal to your slanted tile and K, in other words, cosine of gamma, times the differential area of the slanting tile is equal to the differential area. So if you multiply here and put this on this side, of, that's on the floor when you make your projection. So people call this the area cosine principle, because the one area times the cosine is the one that's down on the ground. And so, for example, if your surface, I'm using the Greek letter sigma as the general name for your surface, when it's a plane, then the cosine would be a constant, because if these are all tiles on a plane, then they all, the normals for them would all be the same vector. They'd all slant the same way. When it's a curved surface, like a dome, say, then, of course, as you go from tier to tier of tiles on the dome, your normal is going to have a different orientation, and your gammas would be changing. So if it's a plane area, then your cosine gamma would be constant and your angle would be. And so you could either say that the ds is the differential area of the projection divided by cosine. Cosine possibly could be negative, so you need an absolute value, because area wouldn't be. And of course, 1 over cosine is secant. So your secant is actually this magnitude of your gradient of z minus f of xy. And so you can call that the projection factor, or it's the ratio between the coordinates that you're using when you have your parameterized surface and the coordinates that go with the plane into which you've projected, say x and y typically. And these might be x and y, or they might be r and theta, or theta and phi, and so on, and we'll look at some examples. So in general then, the parameterized surfaces that are traced by the tip of a vector, I'm using capital R for this vector. Now that vector is, if you go back to the maple that we looked at, when I say go to the front of the maple again, when I type plot 3D, and then I have the vector r cosine t, r sine t, r square, capital letter R is that vector, which typically, using maple, we'll be thinking of it as a Cartesian form vector usually, although it can be something else. So the parameters most often will either be x and y, or r and theta, or theta and z for the cylindrical coordinates, or phi and theta if you're doing spherical coordinates. And so, for instance, if you're using parameters x and y with the surface traced by a capital R then that looks like this, your partial of r with respect to x gives you 1, 0, and f sub x. Your partial of r with respect to y would give you 0, 1, and f sub y. And so your cross product of these partials is what would give you the NDS. You notice that when you do the cross product here, this is that line, and this one is that line. So what the cross product of the partials from your parameterization gives you is the same thing that you get if you approach the problem arguing about comparing the areas of tiles that are on a slant to the areas of their projections down here. So I started out this way, trying to make an intuitive argument that goes back to our chapter 14 with the curve down here and the companion curve up here and the partial derivative and so on like that. But you get to the same thing following an approach that you can generalize by saying, well, we have our parameterization that'll draw a surface. And we've looked at the maple to see that, yes, it really does it. And then we take our partials with the variables that we're using in our parameterization and take their cross product and multiply by the differentials of the two variables. So this gives us a vector area of the equivalent of my green tile. And then we have an approach here that we can generalize when the parameters are not x and y, but are two of the cylindrical or two of the spherical coordinates. And of course, there are other coordinate systems out there that we don't study in the book and so on, but there's more of this in the knowledge of mathematics, let's say, as a science, than we're going to do. So suppose your surface is a sphere. The radius is A, and the center's at the origin. So in Cartesian form, this is the equation of your sphere. And the radius is A, and now with radius fixed on the surface of the sphere, so A is constant, then your parameters would be phi and theta. Remember, the phi is the co-latitude down from the North Pole, and theta is east longitude if you were on the surface of the Earth and started at Greenwich, England, and went east from there. So, and as I've been saying this morning, even with variables that are from spherical coordinates, if you're setting up your R vector to be like this, you're writing X in spherical coordinates, Y in spherical coordinates, Z in spherical coordinates, so it's a Cartesian type vector. So let me remind you about that with this handout. We did this once, and you got this handout once, but like most things, out of sight, out of mind. So, if you remember, I had the drawings on the board, so if you're looking at the spherical coordinates, which is the upper picture, you think of the box, which is d rho, the blue, the rho d phi, which would be the red, and the rho sine phi, which is the r, the radius in green out from the z-axis, and then the d theta. So r d theta would be the green arcs. And then we said that we think of the volume as the differential volume as the product of rho sine phi and rho, and then d rho d phi d theta. And we were doing triple integrals with that sort of thing in mind. Well, now, what I'm trying to show you is that that's related to this business of taking the partials of your parameterization vector capital R with respect to each of the two variables that you're actually using, which are the phi and the theta, and doing their cross product and taking the magnitude of that. So here's my R again. I'm parameterizing the surface of the sphere with radius A using phi and theta parameters, and it's Cartesian because this is x, this is y, and this is z. So then my coordinate ratio or projection factor, which is like the secant of the angle there, is the magnitude of this cross product. So take a look at it while I fill some more paper. So if you do this cross product, what you'll find, you see, you have to take these two partial derivatives and then set them up to do your cross product in the same way that we have been as our 3x3 determinant. What you'll come out with is this vector. And I don't have the board space to go through all that, but this is what you will get. And if you notice, then a square sine phi is a common factor. The sine phi is squared in this component. It's squared in that one, but it's not squared here. And while you might reasonably believe it's just that I made a mistake, this particular time I didn't. Okay, that's not saying I never made one. Okay, I have two children, so obviously I've made mistakes, right? Okay, so you take the a square out and you take the sine out, and what does it leave you? Sine phi cosine, sine phi sine of theta, and there is a cosine of phi. And then if you work with the magnitude of this, remember what you do to get the magnitude is you dot the vector with itself, and you see you'll have a sine square phi, cosine square theta, sine square phi, sine square theta, cosine square phi. So you have a common factor of sine square phi with this term and this one when you squared. So you can factor that out. You'll have sine square phi there and cosine square phi there. And so you'll get down to something that looks like this, you see, when you've dotted this vector with itself. And you have this factor out in front. So you look at the sine square phi in these two terms, and you factor that, and the other factor is cosine square theta plus sine square theta, which is 1. So then you have sine square phi plus cosine square phi, and that's 1. So this whole thing is 1. So what you get is the a square sine phi, if you've done this cross product, and then d phi d theta. You're doing that just the same way that I did this over here. And so notice that what I get for my projection factor or coordinate ratio will be the a square sine phi, and then you'd have d phi d theta. So what we presented first as a geometric sort of thing it actually really comes from doing the cross product of your parameterization, where you've taken the partials with respect to the two parameters. You take the cross product of those and take its magnitude. So then when you have found the projection factor or coordinate ratio, you can get the area of some portion of your surface. So this is A for area, and this is on the surface, as the integration with the limits on your two coordinates you're using, which are the two angles here, if you're on this spherical surface, of the coordinate ratio, which is the a square sine phi, between, it's the ratio between the spherical coordinates that you're using as your variables, phi and theta, and the Cartesian coordinates, x and y, that you replaced in this Cartesian vector with the spherical coordinates. And so this cross product is the a square sine phi when it's the spherical surface. And so then you're integrating with the variables that are the same ones that you've used here as your parameters. So you integrate this with phi. Okay, you integrate sine phi with phi, and you get minus cosine phi. Limits on phi, if you want the whole area for the surface area for the whole sphere. Remember, phi comes from North Pole to South Pole. So it goes down if you thought of the Earth as a globe, where there's typically a globe that's designed to be put on somebody's desk or table, something like that. There's typically a frame that holds it, where the frame is on one side and it's mounted North Pole to South Pole and on a tilt a little bit in that frame. So the phi then is 0 to pi, because your frame is just on one side. If it were a spray rig and you had it on both sides, if the Earth made one full rotation, as it does in the day, then you'd paint it twice if you had nozzles both on the right side and on the left side. So to not paint the Earth twice, either the phi has to be 0 to pi and not 0 to 2 pi, or else the theta would have to be 0 to pi instead of 0 to 2 pi. So limits on phi then, so you have the minus from the integration, cosine pi minus cosine 0, that's minus 1, so you got a minus 2 times a minus, so you have 2a square, and then theta 0 to 2 pi, so you get 4 pi a square, and that's the surface area of the sphere. So you see this, finding this coordinate ratio out of the magnitude of this cross product of partials actually does give you the right answer for the area, surface area of the sphere, if you're working with spherical coordinates. Now we'll go to the other end and see how it works with cylindrical and Cartesian coordinates. You see that if you're on the surface of a cylinder, then you might imagine that the R for the cylinder is some constant A, and then use the theta and z as your parameters, then you'd have something that looks like this. Again, this is a Cartesian form of your vector. This is x, this is y, and this is z. And so if you do your partials with the two parameters that are your variables, from here you get this line, and from here, partial with z, you see you get 0, 0, and 1. So then if you do the product of the partials, work out the cross product again, and you'll get this vector. And then you see the magnitude of this will be just the a, because you'll have a square cosine square plus a square sine square plus 0, and then you factor the a square and say cosine square plus sine square is 1, and the square root of a square then is your magnitude. So then the surface area of a cylinder, if the radius is a and say height is z equal 1, again I use this symbol for the area of your figure that's on the surface, and I'm using the Greek s, the sigma, for the actual name of the surface if I need it. So this would be, if my z limits are 0 to 1, 0 to 1, and then 0 to 2 pi for the theta. So you see we're using theta the same in cylindrical coordinates and spherical coordinates, the 0 to 2 pi. And that's why they chose then limits 0 to pi on the phi in the spherical coordinates. So this cross product would be this one, which would be a, is a v d theta dz. See, this same argument is why if you go from xy to polar coordinates, the dy dx goes to r dr d theta. When we first did polar coordinates, I had a drawing approach like the one that I was showing you with the three-dimensional things for area in polar coordinates. But where you really get it is out of this magnitude of this cross product. And so then when you integrate with theta, 0 to 2 pi, you get the 2 pi. The z, if it's just height 1, just gives you a 1, and then the a comes from your projection factor, or coordinate ratio. And this would be the correct formula for the surface area on the cylinder. So, as I've been telling you, when you write your parameterization like this, with x of the two parameters, whatever they are, which could be theta and phi, or in this case they are theta and z, and y of those, and z is a function of those, you're assuming that you're working with Cartesian coordinates. And as I've said, and as you saw with the maple handout, we either have to do this or do sphere plot if it's spherical, or cylinder plot if it's cylindrical, if you don't mean that you're working with a Cartesian type vector. So look at problem 17 in 16.5. If you have your book with you, you can look at what it is. This dries surfaces also. So, problem 17, if you happen to have the book and look at it there, wants the surface area, which again I'm calling A of S, for the portion of the plane which is inside the cylinder, which has radius 1, and axis of symmetry is the z-axis of the cylinder. So here would be my z-axis, and the axis of symmetry of my cylinder, and here is the portion of it that would be, if x is where my left hand is, and if y is over there, then the floor here would be the first quadrant. So if you were thinking of three-dimensional space, this is the part of it that's in the first octant. And this cylinder would go on around there, and of course the plane would continue so that the high end of the plane, see this plane is, if you think of y plus 2z equals 2 as a line in the yz plane, it's a line like this that would be on this slant. So over at minus 2 for y, you would have the high point of where this slanting plane would be intersecting the cylindrical wall. So I haven't drawn the whole picture, but this is about as much of it as I can draw, I think. So then solving this for z, you have z is 2 minus y, so you could use z in your parameterization. If you want to use the cylindrical coordinates as your parameters, you can write the z in terms of the y. You remember, if you're going from Cartesian to cylindrical, x is r, where r is your radius, cosine theta, and y is r sine theta. So then that would let me express the z, which would be your height from the floor, in terms of y, and therefore in terms of r and theta. So that's what I'm doing. I'm using a Cartesian type vector here. This is x, this is y, and then z is 2 minus y, which is the same y, over 2, because that's the plane. And so what we're after, we're not trying to get the volume of the figure, we're trying to get the area of that much of the plane that's on the slant, you see. So we do our partial derivatives and the cross product, and we get this. And then the magnitude of our cross product, we're dotting this with itself, and that'll get you r square over 4 plus r square, so that'll get you 5r square over 4, and then you take the magnitude of that. So the square root of 5r square over 4 is root 5r over 2. And I'm thinking, of course, of r as positive, which is the square root of r square. So we want the portion of the plane where the angle, what I have shown here is the portion where the angle would be 0 to pi over 2, and where the r would go from 0 to 1. When r is 0, you're in here at the center, and when r is 1, you're out here on the rim of this cylinder, r equals 1. So if you want the entire area, then instead of going 0 to pi over 2, you're going all the way around with the part that I haven't shown. So I have 0 to 2 pi, and then 0 to 1, and then this is my projection factor. So it's the same thing as the secant of the angle gamma between the normal to this plane and K. And since it's a plane, that angle is a constant then. So if you use these as your parameters and do this integral, you'll get pi root 5 over 2. You can see that this is not a difficult integration. RdR will get you r squared over 2, and put in your limits, and then theta, not related to r, will just put in a 2 pi. So then let's look at 23, which is in the maple. So you go to the back side of the next to the last sheet of paper. And you see a picture of 16.5, number 23. It shows the top. There's this cone that's underneath it. I guess where I typed problem 23 in is on the bottom of the front side of the next to the last sheet of paper. So I have plot 3D, r cosine t, that's your x, r sine t, that's your y, and then z is 2 minus r squared. And so that would be the surface that's in this color if you were coming on down. Now what the problem wants is the portion of this that's up above where the cone that starts out at the origin comes out and intersects this cap, which is a parabolic sort of surface that's opening downward. So what we're after is the surface area that's above where I have my blue curve of intersection of the two surfaces. And so what I'm showing really is what would be the top part of it. And so you see the figure on the back side. And then if you use cylindrical coordinates, I did it again using cylindrical coordinates. So then they would be r and t, and 2 minus r squared, and chords equal cylindrical, and you have the same picture. So then you see what I've typed. To compute the surface area, you need the projection factor in the form that's appropriate to using cylindrical coordinates. And so then I have r again, and then I am doing the derivative, map diff, that's formula 2. So there's your partial with r, form line 2 at the top of the back sheet of paper, and then partial with theta is line 3, and then the cross product, and I simplify the cross product. So I have my 2r squared cosine, 2r squared sine, and r. And then the magnitude of that is this projection factor. So I'm dotting line 5 that I've called K, and then I'm taking the square root, and you see line 7 is my projection factor. So if I'm looking at it here, what I am doing is the magnitude of the cross product of these partials, and as I showed you with the maple there, you get 4r4 plus r squared. So when you take out your common factor of r squared, you have its square root, and I'm assuming r is not negative, times the square root of what's left, which is 4r squared plus 1. So the area then on the surface up here is the projection factor, or coordinate ratio, whichever you want to call it, times the differential area, which is the product of the differentials in your coordinates, dr d theta. And then turns out that your that your boundary here is r equals 1. See, I get that from the work here. The problem wants the area for the cap, which is where my hand is, cut from the paraboloid by the cone, which is this in the violet color. Okay, so that's z equal r, and this is z equals 2 minus r squared, because x squared plus y squared is r squared. So you set them equal. R equals z equals 2 minus r squared. So collect your terms. The r squared and the r and the minus 2 then would equal 0, and factor. And remember, your r has to be positive, so you take this factor, not the minus 2. And so if r is 1, then z, if you go back here, z is 2 minus 1, so z is 1. And when r is 0, then z equals square root of r squared is 0. So as r goes 0 to 1, the z is going to go from 0 up to 2. Z is going to go from 1, rather, up to 2. So what we have then is the integral 0 to 1 on the r and 0 to 2 pi on the theta. And if you do that, you see you have a u substitution type problem. Call this u, then the du is 8 r dr, so the r dr is the du over 8, and work out your integral and you'll get what the book has and what Maple says it is. So this again is an example of doing the area as some part of a parameterized surface by getting the projection factor between the differential area using the variables that you've used in your parameterization, gets you the ratio between that area and the area of its projection on whatever surface you're using, where the two parameters are your variables. And so let's look through the rest of our Maple here before we go. We looked at the first two sheets of paper with problem 1, and then with problem 2, notice at the very bottom of the back side of the second sheet of paper in your handout, what I did was plot 3D. I did r cosine t, r sine t, 9 minus r square, and chords equal cylindrical. So you notice that if you say that you're using cylindrical coordinates, you get the picture for 16.5 number 2 that's on the top of the front of the third sheet of paper, and that's a very different picture than the picture for 16.5 number 2 that's on the back of the second sheet of paper, just above where I said notice the difference between the graphs when we put in chords equal cylindrical. You get, if you have done this problem as intended, using your vector as a Cartesian vector, r cosine t for x, r sine t for y, and 9 minus r square, you see the picture, the paraboloid opening downward. If instead you treated those as if they were cylindrical coordinates, you get something, but what you get isn't the same. So it's important to keep straight whether you're really trying to do something in cylindrical coordinates or whether what you're doing is really Cartesian, where you're using the cylindrical coordinates as parameters, but it's still Cartesian, which is what you're normally going to do. But if you want to get it right and use cylindrical coordinates, see what I've done next. For the first one, use r instead of x in terms of r and t. And for the second one, use t, or theta, instead of y in terms of r and theta. And then the z is 9 minus r squared. And turn the page and you're back to your paraboloid thing again. And if you did the thing with Cartesian coordinates, x, y, and z in terms of x, y, you'll get something that's a portion of the surface. The problem with trying to use Cartesian coordinates, x and y, for something that is circular like this is that you see you get these scallops. You get part of the graph, but you don't get all of it. And then finally, if you do implicit plot, you can check what you're doing, because implicit plot will give you the picture all right if you take enough, if you allow enough for your x range, your y range, and your z range. Then I've done problem 5 using Cartesian form and the cylindrical coordinates for the parameters, and you see the same thing back. And then finally, if you use the cylindrical coordinates, so I'm kind of doing the same thing over and over here, but they're just applied in different problems. And then the last one is problem 8, where I've used the spherical coordinates. I'm using p for phi. I'm using t for theta. And I'm working on the surface of the sphere, you see. And that radius of your sphere is square root 8. So I'm putting in the square root 8 the way you put in a letter A, say, or something like that. And so what I'm getting is part but not all of the sphere, because my phi is not going all the way down to the South Pole. It's going from the North Pole to 45 degrees south latitude, if you wanted to say it like the Navy would say. And so we see the portion of it, and then you could do it in spherical coordinates, saying coords equal spherical, your radius, and then T for theta and P for phi. And you see you do get the same picture using spherical coordinates if you set your vector up for it. And then that's back to the problem 23 that we did. So what we'll do tomorrow then is the what are called surface integrals, where they're like line integrals, but with line integrals you just add the one parameter that you got from your curve. Now tomorrow we'll have two parameters, typically the theta and the r, or the phi and the theta, something like that, and then we have our parameterization based on what the surface is. So that's what we'll do. So I remind you then that the first of the 2 days for the final is 4 weeks from today. So we're getting there. And finally, we are done having to listen to politics for a while, which is a nice Christmas present, I think. So with the final, it's there's 25 questions, and about a third of them, I think eight of them are multiple choice, I think, and that's about a third. And the others are what you would call short answer. There's a cover sheet, and there's a box, fairly small, for each of the 17 that are short answer. And you're supposed to get an answer in that box, and then there's space in, it comes as a booklet, and there's space in the booklet to show more of your work. And my idea is that you can come work on it on Thursday until you're sick of it, but you'll know what all the questions are at that point, and you can go home and think about them and come back with renewed vigor on Friday. There's a chemistry class in here, so you can't stay all day, but you can get here as early as you like and stay till about 10:30. That'd give you typically, say, 6 hours to work on the thing, and that's more of your life than you should throw away on anybody's dumb test. Okay, so I'll see you tomorrow.